Hello and welcome to lecture 19. It's going to be the final lecture for chapter 7. It's going to be a very short lecture, but the topic is still important, but luckily it's just one idea. We want to learn how to read a potential energy curve. Well, I should say that's kind of the one idea. The other idea is the formula that tells us where that curve comes from, okay? The calculus definition of the curve. All right, but here we go. Here is the curve in question. All right, the idea is that the vertical axis is potential energy measured in joules, and the horizontal axis is displacement. Okay, let me add some labels to this. Okay, so all we're looking at here, as I said, potential energy and displacement. Okay, this is an example of a potential energy as a function of displacement. This curve right here. Okay, I've highlighted a bunch of ideas on that curve, but this could represent a particle moving through space, and these being some sort of gravitational attraction points. It could also literally be a roller coaster, like along its length, like function of its length, right? Where these could be low points, right? Where gravitational potential energy is converted to kinetic energy. Okay, so that's what examples of what it could represent. Okay, notice that it is not time; it's displacement. Common misconception. There's some terminology that we want to get out of the way in terms of how we read this this graph, this chart. All right, one is the idea of a turning point. So a turning point is a transition from a neutral equilibrium to some state where potential energy is going to be changing as a function of x. Okay, so it's a point where the slope changes from 0 to non-zero. Right, so there's one right there, the green dot. There's another green dot. Those are turning points. Now, right, changing from 0. Well, 0 is neutral equilibrium. So neutral equilibrium is not a point; it's actually a region. So wherever it's flat and it continues to be flat, so there's essentially no functionality between potential energy and x, or potential energy is independent of x, right? Where it just stays flat. That's a neutral equilibrium, okay? So that's where the slope remains 0. All right, so now the more interesting bits, stable equilibrium and unstable equilibrium. So it's as simple as this. A stable equilibrium, being these orange dots here, they represent low points in the graph, okay? Whereas unstable equilibrium, which is just the one purple dot in this case, well, that is a high point. It's a local maximum for purple dots, unstable equilibrium, and it is a local minimum for the orange dots, stable equilibriums. Okay, now here's the thing. That's great. That's a great just way to memorize the graph, but there's a deeper understanding, and that's a simple idea that the tangent line of this curve, its slope, so the slope of the tangent line is force. Okay, right, unit wise it makes sense because we're looking at du dx. All right, well, taking the units of potential energy and dividing them by x, you get the units of force, because after all, joules are kilogram meters squared per second squared. So if I divide them by meters, I'm left with kilogram meter per second squared. Well, that's a Newton. Okay, so right away the dimensions check out, and also the concept is sound. We'll talk about what it represents. Okay, so the slope is force. Here's the thing: if the slope is downwards, that represents a force in the positive x direction. I kind of drew it like a vector here. Okay, so if the slope is negative, then the force is positive. So if slope is negative, then force is positive. So they're always opposite sides. So in a sense, you could say slope is negative force, right? Or you could say, unit-wise, it's the magnitude of force. But we could also say slope is negative force, because it is. And that's something that is easy to forget, but it does make sense. Because think about, just a quick example, this particular stable equilibrium, that local minimum. Well, the idea of a stable equilibrium, as the name implies, means that if you get pushed away from it, then you return back to it. It's like being at the low point on a roller coaster, right? If you were to push the car up and release it, it would oscillate back and forth, right? But it would continually return back to that local low point, okay? That stable equilibrium. So, right? Or a pendulum, a bottom of a pendulum is a stable equilibrium. I lift the pendulum up, I let it swing, and it's going to return back to that point, right? And if there's any kind of non-conservative, dissipative force, then it's going to return back to that point and eventually come to rest. But we don't care about that so much, but it does return back to that point, okay? An unstable equilibrium, right? Any push away, and it's never going to come back, okay? So now back to the forces that I said I think is a good example. So in the case of the stable equilibrium, if I deviate, if I perturb my system, my object, which is represented by this graph, away from that point, there's going to be a force to push me back towards it. Okay? So I push away, but there's a restoring force. If I go in the positive x direction, but away from the stable equilibrium, well, then there's a force that wants to bring me back to it. Okay? It would apply to springs too, right? There would be a restoring force to bring me back to that point. Okay? That's a stable equilibrium. But that means whatever my sign of displacement is, the force always opposes it, which is why the force is equal to the negative of the slope. Okay? So let's see it right there. Okay? Because after all, the tangent line is, in calculus terminology, just the derivative. All right? So that means that force is the negative of the derivative of potential energy with respect to x. It is the negative of the tangent line. Okay? Every time. Now, this equation completely matches up with that graph, right? That's the understanding that I want in terms of the calculus and the graph. Okay? But there's one other idea, is we can apply it to 3 dimensions. When we apply it to 3 dimensions, I won't show a graph. It'd be like a surface. Okay? Well, we have a surface in 2 dimensions, right? Where the and the z-axis is represent the potential energy. If we're truly talking about 3-dimensional potential energy, there's not a way to actually really represent that graphically. Just think about it as like a plot of points, each one having a value, which is the scalar energy, the scalar value of potential energy. It'd be like an array of little points of information. Okay? But the idea is that less graphically, more mathematically, broad idea, you can apply this derivative to each component of 3-dimensional potential energy with the exact same rule. Okay? And that gives us this second equation. So again, all I'm doing is saying, okay, well, I'm just going to consider what's happening in x and take the negative of the derivative with respect to x of potential energy. So there's the negative, and then this is the derivative. Although you might notice that I'm not using a d for derivative, I'm using this other symbol. It doesn't have a name really. It's just a symbol that denotes partial derivative. The reason it's partial derivative is when we have the 3-dimensional case, potential energy is a function of 3 variables, x, y, and z, because we're taking derivatives of its 3 functions, okay? It is a 3-dimensional function. And since we're just taking the derivative of this 3-dimensional function with respect to one of its dimensions, it's a partial derivative, right? Because it's only one of the 3, right? Same when we take the derivative with respect to y, okay? So that's just the notation. But in practice, it's all the same rules. The derivatives, it might as well be the same, okay? But every one of them is a negative. I could have distributed the negative in, but we don't. I factor it out, okay? And then, but it's the same idea, just applied to 3 dimensions. And in practice, you just treat one at a time. Okay, you do x, then you do y, then you do z, and then if you were reporting a vector at the end, because after all it is a force vector, you would just make sure to tack on each one to the appropriate I hat, j hat, and k hat. I have an example where I'm going to do exactly that in just a minute. Now the last thing, new thing, you may not have seen it, is that this notation, taking a series of partial derivatives with respect to x, y, and z of a function that has multiple variables, and specifically x, y, and z, it's called the gradient. So essentially, this operator, right, all 3 of them together, is that symbol, and that is the del symbol, but it's also called the gradient. Okay, and then it's a negative because it's the negative of the derivative. Okay. All right, let's do examples. They're pretty straightforward. Okay, so the first one's probably the hardest. Notice there's only one type of problem. It's problems that involve using the relationship between force and potential energy for a varying force. And a varying force is a function of x. Okay, all right. So a large gas giant orbits closely around a pair of binary stars. That's the premise for the problem. The potential energy of the planet is given. Okay, so this is a potential energy function in 3 dimensions. And what we're going to do is then we're asked for the force acting at particular values. Okay, so all we do here, it's very formulaic, is we just take the derivative of each of these functions one at a time. Okay, so that's the initial notation. In practice, what we're going to be doing is taking the derivative. Okay, so I've done it already. So when I take the derivative of 1 over x, it becomes negative x squared. All right, so they just review your rules of polynomials and their derivatives. Okay, but when we take a derivative, you always reduce the power of the exponent by 1, and since here it was x to the negative 1, then after the derivative it becomes x to the negative 2. which is the same as just writing x squared in the denominator, okay? And then you have to pull the -1 in front, okay? Same exact thing here, pull the -1 in front, all right? And then here, it goes from 5/4 to 9/4 because it's 1 lower, and then you pull the -5/4 in front, okay? Furthermore, all the negatives are from just doing the derivative. This negative, so this negative here is from the fact that this one is the only one that's negative to begin with. And then the last negative is that because all the derivatives, are here. All the derivatives are taken, but then multiplied by -1, I left the negative factored out. But then I'm going to distribute it in, and we distribute it in, our x1 becomes positive. And again, the reason it became positive is because one of our negatives is from doing not the antiderivative, but from actually doing the derivative, right? Pulling the power of the exponent in front. The other negative is just from the definition that force is the negative of the tangent line, okay? So the negative cancels, the negative cancels, the negative cancels when there's a leftover negative because this one was negative to begin with. So they essentially retain their signs, okay? And then we just go on. So force at the particular coordinate is we're just going to plug it in to each one respectively. And that's what I do here. And then we get a number. And by the way, the numbers are really small because I'm squaring a really big number for the distances. So it's a big number. I mean, there are big forces, but there are even bigger distances, and we're squaring them. So when everything's said and done, our forces are quite small. Okay? All right, but that's the idea. Okay, that's how you do it in 3 dimensions. All right, so a couple concept questions. So below are a set of axes on which you are going to draw a potential energy curve. By doing experiments, you find the following information. A particle with energy E1 oscillates between D and E. Okay, well, so let's, here, actually, just fill these in. So here we go. So this would be oscillating between D and E. Because the idea is that these two energies must be equal. So a particle would essentially be trapped and bounce back and forth between those points, right? Because remember, again, the vertical axis is energy, the horizontal axis is distance. Okay, so this would be a trapped particle, like a particle trapped in a box, bouncing back and forth. But if we were to energize the particle enough, well, then it would be able to get out of that, be free, but it would hit another energy barrier. Because up into E2, we're told that it'd be trapped in there. Okay, so a particle of energy E2, so greater energy, would bounce between C and F. Okay, and then we get onto the next one, which is then trapped. So now we make something even more energetic, all the way up to it could be as big as E3, but we're told it's trapped between A and G. So it's just going to bounce back and forth there. Okay, but here's the thing, that it has enough energy that, let's see, did it get split? Oh, I did, excuse me. So there's a last line here. I knew there was one more piece of information. I did not notice that. It's a formatting error. So here we go. A particle with energy E4 enters from the right, bounces at A, and never returns. So if you take a look there, the idea is that something with energy E4 would be able to come in from the right, so this side, and then it gets there, and instead it's going to never return. So it basically bounces. So there's enough potential energy here to stop it, force it to turn around, but then there's nothing to stop it on this other side. So that's why it just takes a one-way journey on its way out. Okay? So with that information, we can connect the dots and draw the curve. Okay? And notice this is all the criteria. Trapped, right? At all these different energy levels, right? Kind of trapped, forced to bounce around, essentially roll back and forth. You can think of it as a ball rolling back and forth in a dish, right? Where these are the heights, the edge of the dish. You could think of it as an electron trapped in some sort of quantum state, right? So they're always interesting ideas. But here, it goes in, but then it's able to come back out because there's nothing stopping it on the side. There's no other energy barrier. That's the idea where E4 is asymmetric. Okay? All right, last concept question. The graph shows the potential energy curve of a particle moving along the x-axis under the influence of a conservative force. So don't worry about drag or friction. All right, so I'm going to do these first 3 together, A, B, and C. So here we're just looking at the intervals where the force on the particle is to the right. So if the force is on the right, then the slope is positive. So this green is positive slope, and this green is positive slope. Because remember, it's the negative of the tangent line. So positive slope means the force on the particle must be to the right. Okay? To the left. So the green ones, the force is to the left. Okay? So all positive slope means negative force. Okay? Negative force would point in the negative x direction. So positive slope, negative force. Okay? Positive slope, negative force. Okay? Points this way. Okay? But then the yellow ones, those are the ones with the negative slopes, and they have positive forces, ones that point that way, to the positive x direction. Okay, remember it's just the negative of the tangent line. I think we get it. And then the red circles are values of x where the magnitude of the force is maximum because they're inflection points. They're simply the instantaneous point where the tangent line is steepest. Okay, but that's also the definition of an inflection point. Okay, and then the last two, D and E, at what values of x are the positions of stable equilibrium? So stable equilibriums are local minimums. So there's two of them, the two pink ones. And then at what value or values of x are the positions of unstable equilibrium? Okay, there's just the one, the gray one right here. It's the high point, okay, the local maximum. Okay, so now we're going to do another one, which is a more complex function, but unlike example one, where we had to deal with 3 dimensions with simple functions, this one is just one-dimensional. Okay, so we're given a potential energy curve for a 2-particle system. All right, and then we're given the coefficients. Okay, and then we are asked what is the equilibrium separation of these 2 particles. All right, so here we're actually then we not just solving for the derivative, not just expressing, say, a force function that corresponds to this potential energy function, but then actually doing something with it. Okay, because then we have to actually find the stable equilibrium, which means just essentially setting that function to 0. But let's see why that works. Okay, so here we have just the definition, okay, for force as related to a one-dimensional potential energy function. Okay, and then here is our potential energy function. So we're just going to take its derivative with respect to r, because that's what the variable is labeled here, not x or y or anything. Okay, and so we're going to do that. That's all I've done here. Notice that it's the same sort of thing, since this is, again, the powers are negative. The negatives cancel out. Okay, and then we're going to find the equilibrium by setting this function equal to 0 and solving for r. Okay, and when we do that, which I would do graphically or with a computer algebra system, there's our value. Okay, and let's take a look at the graph. Right, here it is. Right here is our local minimum. You can see the value corresponds to just about 0.02 on the x-axis. Okay, here let's add some information. Right, there's the function that I graphed. This is potential energy. All right, and there's that horizontal tangent line. Horizontal tangent line meets the criteria of having 0 force. 0 force means equilibrium. Okay, so right, there's no force. It would stay at rest right there. All right, here is it zoomed out a bit, but you can still see it. Okay, so you can still see that local minimum. Okay, so then the question is, how do we know, does this position represent a stable or unstable equilibrium? Because right, the fact that we set it equal to 0 could be a unstable equilibrium, because you'd still have a horizontal tangent line, case in point up here, you'd still have a horizontal tangent line if it's a high point. Okay, we can see from the graph that it's a low point. So you could say, oh, well, from the graph we know it's stable. But you can also do what's called the second derivative test, which is just take the derivative of the force function and then just look for the sign of that derivative if you plug in the local extrema, which in this case, again, was a stable equilibrium. But if you just plug in the equilibrium value, not knowing if it's stable or unstable, plug it in, check for its sign. In this case, it's greater than 0. If it's greater than 0, that tells you that the curvature is positive. Positive curvature means low point, means stable equilibrium. Okay? So, I mean, you've probably seen that in the math class, right? The whole idea of second derivative test, but now we have a physical meaning for it, stable equilibrium. Okay? Well, I hope this has been interesting. Like I said, it's just one idea, but it's an important one. It's a big idea, but hopefully, that since it was kind of concise, it made sense, and you could get a lot out of this lecture. But important thing is I want to say thank you for watching, and let me know if you have any questions. Bye for now.